Welcome to Lecture 13 of Physics 506. This is our second lecture on the addition of angular momentum. We're going to start by examining the simplest case concretely. That's the case where J1 is a half and where J2 is a half. Because the total angular momentum can go from J1 plus J2 down to the absolute value of J1 minus J2, you see the two possible total angular momentum states are big J equals 1, we call that state a triplet, and big J equals 0, we call that state a singlet. Those names come from the fact that when J equals 1, there are 2 times 1 plus 1, which is 3 possible states, and when J is equal to 0, there's 2 times 0 plus 1, which is 1 possible state. Of course, the J equals a half has 2 states. If I combine 2J equals a half, I have 2 times 2, a total of 4 states, so that counting works out just like we showed it must work out when we worked out the general results of the counting in the previous lecture. So obviously J1 and J2 are a half. I mean, that's given at the beginning of the problem and they stay that way. So we're going to drop including the J1 and J2 in the notation, and we're going to just take the state JMJ, J1, J2 and just write it as JMJ. Now, we also know that the state that has MJ equals 1 plus 1, there's only one state that has MJ equals plus 1, and that state must also have J equals 1 because MJ can never be larger than J. So that state is the state where M1 is a half and M2 is a half, or as we like to write it in a shorthand notation, the state up, up, where the up arrow indicates that MJ is plus a half. Now, we can similarly find the state that has MJ equals minus 1. That state is M equals minus a half, M2 equals minus a half, or the state down, down. And again, both those states have J equals 1, and we've already gotten 2 out of the 3 triplet states. The case that's hard to work out is the case where MJ is equal to 0 because there are 2 possibilities. The state with J equals 1, MJ equals 0 is a linear combination of a state that has M1 equals a half, M2 equals minus a half, plus a state that has M1 equals minus a half and M2 equals plus a half, or as we would write it, alpha times up down plus beta times down up. And I just want to remind you that when we write it in this generic way, the order of where the up and the down appears in the Dirac ket is very important. The first arrow indicates the value of M1, the second one indicates the value of M2, and our job is to find out what is alpha and beta in order to be sure that we're in the J equals 1 state. So I'd like you to think about what is it that we do. If you remember, to get the multiplet, the easiest way to do it is to take the state that has an MJ value that's 1 larger and hit it with a lowering operator, a total J minus. So that's what we're going to do. Now remember that when J minus acts on a state J equals 1, MJ equals 1. We worked out this algebra before. You get h bar times the square root of J plus MJ times J minus MJ plus 1 times the state J equals 1, MJ equals 0. Now we plug in the numbers. J is equal to 1, MJ is equal to 1. So that first factor is 2. And then if I plug in J equals 1, MJ equals 1, that second factor is 1. So we get square root of 2 times h bar after we act with the J minus operator. But we also can write the J minus operator as J minus 1 plus J minus 2, or if you like, S minus 1 plus S minus 2. And then remember that S minus acting on up just gives me h bar times down. The number in front is a 1 when I'm working with spin 1/2. So then S minus plus 1 plus S minus 2 acting on up, up will give me h bar times down, up. That's when it acts on the 1 state, plus up, down. That's when it acts on the 2 state. And that whole thing equals square root of 2 h bar times the ket J equals 1, MJ equals 1. I divide both sides by square root of 2 h bar, and I find that alpha equals 1 over square root of 2 and beta equals 1 over square root of 2. And the state J equals 1, MJ equals 0 is just 1 over root 2 up, down plus 1 over root 2 down, up. Okay, now again, I want you to think about how we find the state J equals 0, MJ equals 0. And in this first case where we've just lowered the maximal state by 1, we just get that state by finding the state that's orthogonal to the one that we found. And if you remember the trick, when I have a two-dimensional vector, if the vector is alpha beta, the vector that's perpendicular to that is beta minus alpha. So we immediately can write down what the state is that has j equals 0, mj equals 0, because it must be orthogonal. It's simply the state 1 over root 2 up down minus 1 over root 2 down up. And again, we tend to write it in that fashion with the minus sign acting on that second term. That's just a convention. Of course, you know, if we multiply that state by any complex phase, it's still the same state. But it's just conventional to write the minus sign on the second term. All right, so we figured out how to do it for spin equals a half. Let's now try to work it out for a more general case, one where the first spin is any arbitrary spin and the second one is spin equals a half. Then again, our two possible j values are j1 plus a half and j1 minus a half. And obviously, again, the state that is j equals j1 plus a half, mj equals j1 plus a half is the state m1 equals j1, m2 equals a half, because that's the only state that has a total z component of spin that's equal to j1 plus a half. In order to find the state that has the same angular momentum but has an mj that's equal to j minus 1 half, we again have to use the lowering operator. And now we're going to plug in again. J minus acting on this state is going to be h bar times the square root of the total j plus the mj. So that's going to be j1 plus a half plus j1 plus a half. And then I'm going to have the total j minus the mj plus 1. That term becomes 1. So we just get a square root of 2j plus 1 times h bar times the state j1 plus a half, j1 minus a half. Now, again, j minus is just j minus 1 plus j minus 2. And all we have to do is now work out what is j minus when it acts on the state. Well, j minus 1 acting on a state that has mj equals j1, m2 equals a half. Again, we have to use our formula, and we're going to get that it has an h bar times the square root of j1 plus mj, which is 2j1, times j1 minus mj plus 1, which is 1. So we're going to now get a square root of 2j1 times the state m1 equals j1 minus 1, m2 equals a half. And then when it acts on the second term, because that's spin 1 half, we just flip the spin and multiply by h bar. So we get h bar m1 equals j1, m2 equals minus a half. And you can see those coefficients are no longer balanced like they were when the j1 and j2 were each equal to a half. But this allows us, we then divide both sides by the h bar square root of 2j1 plus 1, and we immediately get that the state j equals j1 plus a half, mj equals j1 minus a half is given by 1 over the square root of 2j1 plus 1, m1 equals j1, m2 equals minus a half, plus the square root of 2j over 2j plus 1. The state m1 equals j1 minus 1, m2 equals a half. And again, to find the state that corresponds to j1 equals j1 minus a half, mj equals j1 minus a half, we just have to find a state that's orthogonal to it. So again, we switch the coefficients and give one of them a minus sign. And what we find is the state is then given by square root of 2j over 2j plus 1. m1 equals j1, m2 equals minus a half, minus the square root of 1 over 2j1 plus 1. m1 equals j1 minus 1, m2 equals a half. All right, so that really wasn't so bad. It's a pretty general case that we worked out. You're going to be working out on the homework the case where j1 is equal to some arbitrary j1 and j2 is equal to 1. That case is a bit harder to do. And there are two ways in which you can work that out. One is doing it this way, but to get the states with the along the way as you're trying to get the different states, you will find that you will have to apply a bunch of j minuses and other things like that to get all of the states and get everything to work out correctly. It can be a little bit complicated to get all of the terms and to get everything to work using the raising and lowering operators. And so there's another technique that you can use. Some people find this other technique more complicated. Other people love it and prefer this one as the one to use. I'm going to show it to you, and you can decide when you get to the homework which one it is that you want to work with. Okay, before saying that, we also have to figure out how do we get the lower MJ values. And because, remember, we have a whole bunch of other states. that have j equals j1 plus a half and states that have j equals j1 minus a half, because we have all those different possible mj values. And we get all of those just by hitting with a j minus. And then we just have to put in the right normalization factor. The normalization factor is h bar times the square root of 2j1 plus times 2 for the first one. And you can work it out for the second one and the third one and so forth. Those factors change. But what you find in general after you work that out, and I'll let you just carefully go through. I'm going to just move the page up just a smidge. When you carefully go through and work it out for that case with j1 minus 3 halves, you just apply the j minus and you divide by the coefficient that you know you're going to get when you apply the j minus, which is 2j1 times 2. And then what you have to do is you have to work out what that state was, and you have to go in and you have to plug in what that is in terms of the operator acting on the state that has m1 and working on the state that has the particular m2 value. You know, with the m2 value, you can't lower the state that has minus a half, but you can lower the state that has m2 equals plus a half. For the m1, when you look at the different linear combinations, you can lower it in both places. So we end up with 3 terms here. One which corresponds to the lowering when the m1 is equal to j1 minus 1. One which corresponds to the lowering when the m1 is equal to j1. And then one which corresponds to the case where the m1 is equal to j1 minus a half, and I'm lowering the m2 from plus a half to minus a half. Okay, and you have to go through and work out what the numbers are that come out in front for each of those guys. And then you find that there's a simplification. A lot of the terms cancel, and you end up with this final result, which is square root of 2 over 2j1 plus 1. m1 equals j1 minus 1, m2 equals minus a half, plus square root of 2j1 minus 1 over 2j1 plus 1. The state m1 equals j1 minus 2, m2 equals plus a half. And then you can work this out in general. And so the general formula is square root of j1 minus mj plus a half over 2j1 plus 1 times the state m1 equals mj plus a half, m2 equals minus a half, and square root of j1 plus mj plus a half over square root of 2j1 plus 1. m1 equals mj minus a half, m2 equals a half. Okay, you can't immediately see, and it's not obvious that that's the case, but this is the result. And I'm going to show you how we get that in just a moment. Similarly, if you apply those lowering operators onto the state j equals j1 minus a half mj, you'll get square root of j1 plus mj plus a half over square root of 2j1 plus 1. m1 equals mj plus a half, m2 equals minus a half, minus the square root of j1 minus mj plus a half over the square root of 2j1 plus 1. m1 equals mj minus a half, m2 equals a half. You can see that those two states are orthogonal to each other, as they must be. All right, so the other way that we do it is we say that our state j comma mj is given by a linear combination of the two different states that I can construct that have the given value of mj. So that would be alpha with m1 equals mj minus a half, m2 equals a half, plus beta times the ket with m1 equals mj plus a half, m2 equals minus a half. And now what we do is we act the j squared operator on this, and we force it to have a definite j value. In fact, we actually know what the two possible definite j values are. The two possible definite j values are j1 plus a half and j1 minus a half. So we're going to be effectively looking for a eigenvalue and finding the eigenvectors of a matrix. Or you can think of it in those terms, in terms of finding eigenvalues of a matrix, but we know what the eigenvalues are, so you don't have to solve for when the determinant is equal to 0. It sometimes is useful to verify that indeed the determinant is equal to 0 when you subtract the eigenvalue times the identity matrix, just to make sure that you haven't made an error as you've been going through the calculation. All right, so to do this, we have to calculate what is j1 plus j2 quantity squared. Remember, that's the vector, so it involves the j1x, j2x, 1y, j2y, and the j1z, j2z. Okay, but we can also write it as j1 vector squared plus j2 vector squared plus 2j1 dot j2. And then we can write that 2j1 dot j2 as 2 times j1 plus j2 minus plus j1 minus j2 plus divided by 2 plus 2 times j1z, j2z. And now we're going to be looking at acting j squared over h bar squared. We're just dividing by the h bar squared to make our lives a little bit easier so that we're just working with numbers and there are no h bar factors around. And we just go in and we plug in what these results are. So in the state, because we're writing this state in terms of an M1, in terms of a J1, M1, J2, M2, and the J1s are always the same and the J2s are always the same, we know that when J1 squared acts, we're going to get a J1 times a J1 plus 1. And when J2 squared acts, we know we're going to get a 3/4. And then we have to go in and calculate the other terms. The other one that's easy, which is diagonal, is the JZ term, which will just be 2 times MJ minus a half times a half. When I'm acting on this first state with MJ minus a half and a half, okay. Then we have to work out the J1 plus the J2 minus and what that does. There's only one term that's non-zero for each of those J1 plus J2 minus terms because J2 minus acting on the minus state is 0 and J2 plus acting on the plus state, the plus a half state, is 0. So there's only 2 states that come out. And in the first case, the alpha state is a state that involves the J1 plus J2 minus, and you have to go ahead and plug in that coefficient for the J1 plus. It's the square root of J1 minus MJ plus a half times J1 plus MJ minus a half plus 1. And then you have to do the same thing with the term that has the M2 equals minus a half. And in that case, we get first the diagonal terms, the J1 times J1 plus a half plus 3/4 plus 2 times MJ plus a half times minus a half. And then we get the J1 minus J2 plus term, which is going to convert the ket. It's going to change the M1, M2 values. It's going to change the ket to the other ket. And then we multiply by the square root of J1 plus MJ plus a half, J1 minus MJ minus a half plus 1. If you're not able to follow this with the way that I was describing it to you, you really need to pause the video. Take the time to carefully go through and verify this. Go and make sure you know what happens when a J plus or a J minus hits a particular state, and you'll be able to get all these numbers to work out. You'll be able to get everything to work out properly. But please make sure you do that because it's really important you know how this calculation works. All right, we can think of this as a matrix multiplication now on the vector alpha beta. And if I go and I extract what that matrix multiplication is, you find it's a 2x2 matrix. And I've written it out for you here. I'm not going to read it out for you. You see it clearly in front of you there. And we know that the 2 eigenvalues are J1 plus a half times J1 plus a half plus 1 and J1 minus a half times J1 minus a half plus 1. So we know what the eigenvalues are, so you can subtract the eigenvalues from that and verify that the determinant of the matrix is 0. And then the goal is you pick each one of those eigenvalues and then you just solve for what alpha beta is. Now, as you remember, when you find the determinant of a matrix, you really only have to solve for the ratio of alpha to beta because we have a normalization step which will determine the magnitude of alpha, of the vector alpha beta. So you only have one equation you have to solve for a 2x2 matrix. All right, so let's go ahead and do that. We're going to, here I'm going to actually show you that if you don't plug in what those eigenvalues are, you just determine what the eigenvalues are, you get the right answer. So let's go ahead and do that. So we're going to just subtract lambda times the identity matrix. Now note, again, I'm going to re-emphasize for you, you don't have to do this step because you know what the eigenvalues are. But I'm going to just show you to make sure that we didn't make any mistakes along the way, that we do get that when we solve for the determinant of m minus lambda times the identity matrix is equal to 0, that we indeed get the right eigenvalues. Okay, so when we calculate that determinant, you see that you have J1 plus a half squared minus lambda plus MJ and J1 plus a half squared minus lambda minus MJ. So we get J1 plus a half minus lambda quantity squared, which is lambda squared minus lambda times 2 quantity j plus a half squared plus J1 plus a half to the 4th. And then we get minus MJ squared. And then when we look at the cross terms, we will get the square of that square root. So we'll get minus J1 plus a half squared plus MJ squared. You immediately see the MJ terms cancel. which of course they need to because our eigenvalue doesn't depend on mj. Every state with every mj has the same value of the total j. And now we do some simplifications. Okay, so you can see what you're going to get is lambda squared minus 2 j1 plus a half quantity squared times lambda plus j1 plus a half quantity squared times 1 plus j1 plus a half quantity squared. That whole thing equals 0. That's a quadratic equation. We can immediately find the roots. We get j1 plus a half quantity squared plus or minus 1/2 the square root of 4 j1 plus a half to the 4th minus 4 j1 plus a half to the 4th plus 4 j1 plus a half squared. Those first two terms cancel. I have a perfect square. I take the square root. The 4 becomes a 2, cancels with the half. I get just j1 plus a half. So we get j1 plus a half squared plus or minus j1 plus a half. I can factor out a j1 plus a half from that. I get j1 plus a half times j1 plus a half plus or minus 1. That indeed gives us a state that has a total j equal to j1 plus a half and a total j equal to j1 minus a half, exactly like we knew it must. So now we're going to plug in each of those different eigenvalues and solve for the alpha and the beta. So let's plug in lambda equals j1 plus a half, j1 plus a half plus or minus 1. I'm going to just solve them both schematically at the same time. We plug in those values into the eigenvalues. You see you're going to get a cancellation where there's a j1 plus a half term squared that's going to cancel. I'm going to just be left with minus or plus j1 plus a half times alpha. The square root term is going to stay the same. And I have the plus mj. I just bring the beta term over to the other side. I divide by the coefficient of the beta term, and we find beta will equal plus or minus j1 plus a half plus minus mj divided by the square root of j1 plus a half squared minus mj squared. There should be an alpha in there. And that equals plus or minus the square root of j1 minus plus mj plus a half divided by j1 plus or minus mj plus a half, which you can get when you factorize that denominator and cancel one of the common factors and bring it up into the cancel part of one of those factors in the numerator and make the numerator into a square root. Now, to get the normalization factor, I'm actually going to just multiply by that denominator. So I get alpha equals plus or minus some constant times j1 plus or minus mj plus a half, and beta then equals a constant times the square root of j1 minus plus mj plus a half. And then I'm going to add the squares together and set that equal to 1. And you find that the constant is 1 over the square root of 2j1 plus 1. After we set alpha squared plus beta squared equals 1, we bring that into our solution and we get the following table. We find that the state j equals j1 plus a half that has the m2 equals a half or has the m2 equals minus a half. The coefficients are each of those two terms in the table. And the state that has j equals j1 minus a half with those two different states has the given coefficients in that table there. I'm going to write it out in long form in terms of the kets in a table below, but this very compact way of writing the table is the way that you will see these coefficients, which are called Clebsch-Gordan coefficients. This is the way you'll see them presented in tables or in textbooks. So you should become comfortable with figuring out how you go from the table to this expanded version of the table, which I'm going to show you the full version of it in just a second. Okay, so let me go ahead and show you that full version at the bottom here. If we take a look, actually we're going to focus now, I'm going to bring it back up and focus on the first line. You see what that says is that first coefficient gets multiplied by the ket, m1 equals mj minus a half, m2 equals a half, plus the ket that is m1 equals mj plus a half, m2 equals minus a half. And then for the second line, you see that that first coefficient is multiplied by the ket m1 equals mj minus a half, m2 equals a half, and the second number is multiplied by m1 equals mj plus a half, m2 equals minus a half. And this is how we use the table. Now, in the homework, you're going to be asked to make a table for j1 arbitrary, j2 equals 1, in which case the table will be a 3x3 table, so there'll be 9 entries you have to get for the arbitrary values of mj and j1, and you can solve it in exactly this way, but the algebra is quite a bit more complicated than what we did here. So that is really a problem that you're going to want to use your French cooking skills and just do it slowly and carefully, working through each step to make sure you don't make a mistake. You might find that working with the symbolic manipulation routines, as you can find in Wolfram Alpha, may help you get through that algebra without making a mistake, because it's very easy to make a mistake. You should verify that your different states are orthogonal. Again, Wolfram Alpha would come in handy in doing that and so forth, so that you make sure that your actual terms in the table really are correct or have a good likelihood of being correct. All right, that's all that we have for Lecture 13.